Ladies and gentlemen, my name is Maximilian and I'm going to present you Freedom for the SQL Lambda, just-in-time compiling user-injected functions in PostgreSQL. And this was joint work with Jakob Huber, Alfons Kemper and Thomas Neumann. So first of all, why do we need Lambda functions in SQL? We have SQL, which is Turing complete as it supports recursive tables. Queries get optimized before execution, but the statements must be expressed in relational algebra. Then we have hard-coded operators. They are purpose-specific but high-performant. But they require development by a database engineer, which is expensive. Then we have user-defined functions. They allow procedural language statements in SQL, such as PL/PG-SQL in PostgreSQL. But this is not as performant as operators are. Then we have external tools to analyze the data, but then the database system is used as a storage layer only. This makes time-consuming extraction necessary. That's why Hyper comes along with Lambda expressions, and they allow a customization of operators. So what is Hyper? Hyper is a code-generating database system that produces LLVM IR, so IR for intermediate representation code. So here the query plan gets compiled into LLVM IR code. Then Lambda expressions, they are allowed to inject code into regular operators. Lambda expressions are composed of Lambda arguments to identify the tuples and the Lambda body to formulate an expression. An example for this is k-means with an injected distance metric, such as here the Euclidean distance. Here we can see the call to k-means in SQL. Here the two tables as input and the distance function given is the Lambda expression. Currently, Lambda expressions are only implemented in Hyper, and the corresponding source code is restricted. That's why we were asked to implement Lambda expressions inside of an open source database system such as PostgreSQL. What are the challenges when integrating Lambda expressions in PostgreSQL? First of all, we need support for table arguments, so table access inside of table functions is needed. SQL 2016 supports polymorphic table functions, such as shown here. So here we have the creation of a table function that expects a table as input, and then we call the table function with a table as input. But this is not yet integrated in PostgreSQL. Then we also need to support Lambda functions inside of PostgreSQL, so we have to register lambdas as PostgreSQL expression. Then, last but not least, we want to just-in-time compile the Lambda expressions with LLVM. This is supported since PostgreSQL version 11 for expressions. But type and validity checks slow down performance, and also this doesn't allow multithreading with our Lambda expressions. And also, these type checks are not necessary for Lambda expressions. So, how do we implement Lambda expressions and tables as sub-arguments? So, support for table arguments, current approaches are that the table name is given as a string, but this requires another database connection to access the data. So we present two solutions, Lambda table and Lambda cursor. Lambda table materializes the data in a tuple store, and Lambda cursor returns a plan descriptor to fetch the data tuple-wise. How do we support Lambda functions? First of all, we add the keyword Lambda for Lambda function recognition. But the remaining syntax is similar to Hyper. We have Lambda arguments to identify the tuples, and we have a Lambda body to express the function. What did we modify inside of the PostgreSQL engine? So we have one big C struct that holds all information of the Lambda expression. Then, during the 4 execution steps, this expression struct is filled. So the parser, we added some rules for Lambda expressions, like here. Then the analyzer also added a Lambda for type deduction. Then the planner optimizes distinguishes between Lambda cursor and Lambda table, as the second one needs a separate materialization step. And finally, the executor passes the Lambda expression to the table function for execution. How do we use these lambda expressions. First, we have to create a table function before we can call it. So when we specify the table functions, we have lambda table and lambda cursor to indicate that we expect a table as input. Then we have a lambda to indicate that we need here a lambda expression. And access to the input tables as well to the lambda expression happens inside of a shared library that must be written in C. How do we call a table function? The SQL statements are given to specify the input table, and then the lambda expression is given as defined. The lambda arguments identify the tuples, and the lambda body expresses the function. As we wanted to generate the code to achieve a near hard-coded performance, we have these 4 levels of execution. The first one is the interpreted execution that evaluates the PostgreSQL expression with a computed go-to approach. That's the normal way to adjust the interpreted execution. The second one is using the existing JIT optimizations for PostgreSQL, but this only allows a single-threaded execution of our lambda expression. That's why we come up with a custom LLVM wrapper for thread-safe lambda execution. And there we have 2 ways, one with calling a function and one with injecting the code. So and here this figure shows the code injection. So we are compiling the table function with CLang. PostgreSQL gives us the LLVM IR code, and in one injection pass we assemble both to one native code. So here an example of our LLVM wrapper. As I said, the JIT compilation supported so far doesn't allow multithreading in conjunction with lambda expression, as it stores the result of each opcode in fixed memory positions. So that's why we come up with a stack-based build-up of the LLVM structure to allow multi-threaded execution. And here we can see an example for supported opcodes. So here's a tree with a field select and an addition and a multiplication. So this is directly compiled into one operator. So we implemented 2 exemplary table functions. The first one is PageRank, the second one is KMeans. PageRank calculates the PageRank for nodes given a set of edges, so A knows B. As input arguments, the operator expects an input table, so the edges, and parameters like the maximum number of iterations, or the threshold, or the damping factor. And we have 2 lambda expressions, one indicating source node and one indicating the destination node. For KMeans, we need 2 input tables, one for the initial clusters and one for all points. Lambda expression then defines the distance metric, such as here the Euclidean distance, and we return all points assigned with a cluster number. Then let's come to the evaluation. So the setup is we are using our Ubuntu 18.4 machine with 20 cores and 256 of RAM, gigabyte of RAM. We are using PostgreSQL version 11, and we are using the current Hyper version. We are performing 5 test runs. The results were averaged, and the work mem configuration of PostgreSQL was set to 8 GB, so it's only working in main memory. For the KMeans, we benchmarked the operators of the Chicago taxi trip dataset and random points. So the Chicago taxi dataset was about 100,000 of tuples, and we clustered the drop-off locations by latitude and longitude, and we have generated random points, 2 million random points, and we built 10 clusters and performed 80 iterations. As we can see, the performance of operators is similar to those of Hyper, and we achieve a near hard-coded performance in PostgreSQL. And also we can see that it scales with the number of available threads. We benchmarked PageRank with the LDBC social network benchmark with the person knows person relationship by a scale factor of 10, giving about 200,000 of edges, and we are using a damping factor of 0. And as we can see, PostgreSQL has a constant overhead of about 250 milliseconds. This is caused during preprocessing when creating a dictionary. And as we can see, it scales also with number of available threads, but not as well as k-means. To conclude, we successfully integrated Lambda expressions in an open source database system, PostgreSQL. We added support for table arguments in PostgreSQL, and we come up with an LLVM wrapper for just-in-time compiling Lambda expressions. We showed its exemplary usage with PageRank and k-means, and we also achieved comparable performance to Lambda expressions in Hyper. As future work remains to address Lambda expressions directly in PL/PG-SQL. You can find the source code online. That's it from my side, and thank you for your attention.